Okay, have you ever taken a crazy looking integral sent to me by Sid? We've got the integral from 1 to infinity. We've got the natural log in it, and we've got the floor and ceiling functions in here multiple times. Now, my notes are kind of all over the place on this. I have this, I actually threw out one page. I got like both sides on this. I've got yellow notes. So I'm actually pretty disorganized with this one. Hopefully I can figure out a way to explain what's going on with this one. So to get started with this, the first thing we want to notice, I usually want to deal with the floor and ceiling functions first. It can be really intimidating when you have all this floor and ceiling stuff going on. But actually the thing is with the floor and ceiling is a lot of times it actually makes the problem easier. The floor and ceiling functions are always going to return an integer value. So that means everything inside the natural log here is just going to become a constant value. And so really the whole thing's a constant. And so the integral is going to go away. We just need to figure out what these constants are going to be. What are all these values going to be? So what's going to be a good strategy here is just breaking up this integral, separating the lower bound from the upper bound by 1, because that's going to help us turn everything into a constant. So it's going to be like 0 to 1, 1 to 2, 2 to 3, all the way to infinity. Actually, I kind of lied because our lower bound's 1 there, so there is no 0 to 1. So we're actually starting at 1, and then this would keep going to infinity. But I think instead of writing all this stuff out, I think what we'll do is just start by kind of generalizing it. We know we're going to have an infinite number of integrals separated by 1. And then what I can do for that is, let's just do it. Each one of these integrals is going to look something like an integral from n to n plus 1, right? And then what we're going to need in here is we're going to need the floor of x, the ceiling of x, the floor of sine pi x, and the ceiling of sine pi x. So we have 4 values to get. The simple ones are going to be these floor and ceiling of just x. So the floor of x, it's going to round us down to the next highest integer in an integral where our x values are going to be between n and n plus 1. For all these x values, the floor is going to round us down to the lower bound, just n. And then for the ceiling on this, really similar. What's going to happen, it's going to just round us down. All these x values between n and n plus 1, they're going to get rounded up to this upper bound, n plus 1. Now for sine pi of x, it's a little more complicated. We're going to want to look at a unit circle for this. Maybe first, let's just think about it as going from 0 to 2 pi. So like if that's 0, that's pi. This is also 2 pi. When our sine value is anywhere up here, the ceiling function, let's just write it like this. The ceiling function for anything in this region, it's going to round us up to this value, which is just 1. And then when we have the floor on anything in this region, that's going to round us down to this value, which is going to be just 0. And then doing the same kind of thing in quadrants 3 and 4, the ceiling function is going to round us up to 0, and the floor is going to round us down to minus 1. So then the tricky thing here is we can't just get a single value for the floor of sine pi of x and the ceiling of sine pi of x, because it's going to depend which quadrants we're in. What we can do is kind of use these endpoints here. Like this point right here, it's going to be pi, but it's also going to be 3 pi. It's also going to be 5 pi, 7 pi, etc. And this one's going to be 4 pi, 6 pi. And so these values over here, they're always going to have an even coefficient on the pi. And these ones over here are always going to have an odd coefficient. So then what I'll do over here is break this up into the odd and even cases. So maybe let's start with our case where n is even, n being again the lower bound. So when the lower bound is even, it's going to be one of these points here. And so the upper bound n plus 1, that's going to be this point right here. So when n is even, our sine pi of x value, they're all going to fall within quadrants 1 and 2. So we have this case right here. So then the floor function is going to round us down here to 0, and the ceiling function is going to round us up to 1. Then doing the same kind of thing, when n is odd, the lower bound is odd, we're starting here and we're going all the way down to here, which puts us in quadrants 3 and 4. So for that case, what's going to happen is the floor function is going to round us down to minus 1, and the ceiling function is going to round us up to 0. So then with what we have over here to the right, that's going to give us everything we need to figure out our integral for the even case and odd case. So we'll do 2 integrals so we'll do 2 generalized integrals, one for the odd case and one for the even case, and we'll fill it in with all this. Okay, so first looking at our odd case, all I did was just fill in every value from what we have over here to the right. Now you notice we have this 0 here from the ceiling on the sine function. That's going to cancel out right here, so that's just going to be a 0 there. And then because we're squaring everything in the numerator, this minus is going to just become a plus 1. So then we can just rewrite this whole thing, because then what's going to happen in the numerator, this is going to become just n plus 1 squared. But then I can cancel one of these with one of these, and what we're left with, this is just going to become natural log of n plus 1 over n. And so this is going to be our generalization for the odd case. Now let's just go ahead and look at the even case of this. Okay, now for the even case, again, taking all of our values here from the right and just filling in everything here. Now what happened is the 0 term is on the first part, so that piece is going away. We just have a 1 on the end, so the whole numerator becomes n squared. So if we just kind of simplify all this stuff down to n squared, that's going to allow me to cancel one of these with one of these. And then so what we have for our even case is going to be just natural log of n over n plus 1. And so now that we have our even value, let's put this together with our odd value and see what we come up with. Okay, so now that we have our generalized case for our odd and even integrals, we just have to remember what we're doing. The original bounds are from 1 to infinity, so we want to sum all these things up all the way to infinity, turn this into a summation. One thing I want to do is, first, let's just deal with what's happening with the integral. In each of these cases, again, this is just going to be a constant value. We've got no x here and here. So what we're really doing is we're integrating from n to n plus 1 of some constant we'll call c for now. And when you integrate this, you're just the c is gonna come out front. You get c times x from n to n plus 1. You evaluate this and you're gonna have just c times n plus 1 minus n, but this is all just 1. And so in every case of these integrals, we just get back this constant inside. We don't need the integral at all. So the integral is just going to go away completely in this, and we can just consider summing up these constants. And now with the integrals gone, we just want to put this back into a series form, kind of like we have here. But you'll notice this doesn't really make a lot of sense what we have right here. If we use log properties and multiply them together, we get natural log of 1, and the answer is 0. This right here is not quite what's happening, because what we want to do in order to have these together in the same expression is we want something to reflect even n and something to reflect odd n. What we can do is, for an even n, I can write this as, instead of using n, we can write it as 2n. And for an odd n, we can kind of create this as either 2n minus 1 or 2n plus 1. Noticing that's always even, and this is always going to be odd. So what I think I'll do is rewrite this sum. I'll use the 2n minus 1. So when we do it that way and we update everything, for our odd values of n here, 2n minus 1, so this is going to become like 2n minus 1 here, and then this is just going to become a 2n. And then for our even values, if we use 2n, this is going to become natural log 2n over 2n plus 1. But then with log properties, now we can bring these together and it's going to work the right way. So when we do that, we're going to end up with 2n squared in the numerator. And then in the denominator, we'll just leave it as 2n minus 1 times 2n plus 1. And then what we can do to get a sense of it is just kind of start writing out some terms, starting when n equals 1. So the first one's going to be ln 2 squared over 1 times 3. The next one, ln 4 squared over 3 times 5, maybe one more. So we're going to have natural log 6 squared over 5 times 7. And of course, this is going to go on and on forever to infinity. But then with log properties, again, we can actually bring these all together and multiply. So I'm going to write this as natural log of, we have all the even numbers in the numerator, so like 2 times 4 times 6, on and on to infinity with the whole thing squared. And then in the denominator, I think I'll kind of reorder it and like go like 1, 3, 5. So we have odd numbers, 1 times 3 times 5 times 7. And for this other one, we'll start at 3, so we'll have 3 times 5 times 7, again, onto infinity. And then what you notice is this right here is going to be like 2n double factorial when n is going to infinity. Now you could really look at these things as the same thing, but I can write one of them as 2n minus 1 double factorial, and the other one is 2n plus 1 double factorial. It's going to like work a little better for me if I write it this way, I think. And then what we can actually do to simplify this is write this in the product notation. So I can write this with the product inside the natural log. We'll write this as the product as n's going from 1 to infinity. And then writing it this way, we don't have the double factorial. This just becomes 2n squared. And we can write this one as 2n minus 1 times 2n plus 1. And then at this point, you may recognize this thing right here. This is actually the Wallis product. And the value of this is known to be pi over 2. And so just putting this together for our solution of this, we just get natural log of pi over 2. And so before I finish up, I just want to take a quick look at where this comes from. I'm not going to derive it completely, but let's just see a quick way if we can get this value from some other things we might know. Okay, so what I did to get the formulas for this, I went back to my website. I had a quiz called Power Reduction Integrals, and I've done a bunch of videos where I think I did one where like it was like this, but cosine to the 100 or sine to the 2024. When the upper bound's pi over 2, that's the Wallis integral, and then these are kind of very closely related to that. So what we can do is look at this general integral right here that we'll use for our I sub n right here. And then we have the formula for the odd case and the even case. And so this part of the formula here and here, it actually doesn't matter if it's sine or cosine, and it doesn't matter what the bounds are as long as it's a multiple of pi over 2. The one thing that will vary on here is this I sub 0 and I sub 1 value, but those are always really easy to find, right? Because for I sub 0, you plug a 0 in there, you're integrating 1. And then what happens is this value right here becomes pi. And then for our I sub 1 value, you plug in 1. This is just the integral of sine. When you do this one out, this piece right here is going to be 2. Just for this case when we have our bounds like this, we're integrating sine. Now, one thing you'll notice about these integrals, when the n gets large, like some of these ones where I did, if we're doing n is 2023 and then we're doing n is 2024, if you look at a graph of it, the graphs are so similar, like changing n by 1, it does almost nothing for the graph. You could also show this by calculating out with these formulas. You could like formally create this as a ratio of 2 consecutive n values. And what you'll find is n's going to infinity, that ratio is going to 1. And so what we'll do for this is make that assumption that as n's going to infinity, the ratio of consecutive terms, the limit of that's just going to be 1. And so what we can do is put these together as a ratio. So we'll have our odd value. You could do this either way. You could have it either I2k over I2k plus 1, but let's do it this way. And we're saying this ratio is going to be 1. And we're doing that because remember earlier our product was going off to infinity, so it's fair to assume that k is going to infinity here. And then we'll just use these formulas over here to the left. So then our 2k plus 1, I'm going to try to save a step here and write this out. So we're going to have our value for the odd case. And then bringing in our even case, we're going to have this 2k minus 1 double factorial. Flip this into the numerator as a 2k double factorial. And then we're going to have just the pi over here in the denominator. And then so let me just kind of come over here and reorder everything. So we're saying 1 is going to equal, I want to pull out the 2 over pi. So we're going to write this as 2 over pi times everything else. But then this right here, this is exactly our Wallis product value that we had before. We had it in the product. I wrote it both ways. We had it in terms of the product notation, and then we also had this as a limit as k is going to infinity. So if we look at this as a limit as k is going to infinity, and then so what's going to happen when we multiply this w value times 2 over pi in order to get back to 1, this needs to be just pi over 2. Okay, so there it is. Thanks again to Sid for the interesting problem today. Thanks everyone for watching. Have a good day.